Hi, today we're going to start a new unit, organic chemistry. As a brief do now, I want to give everyone a chance to remind themselves of how Lewis dot structures work, particularly of covalent compounds, because that's really at the center of all of organic chemistry. So by all means, if you need to hit the pause button, take some time, draw these structures, and then answer these two questions beneath it. Great, I'm going to get started, save a little time. In drawing these, hopefully you figured out that the carbon ends up going in the middle, making 4 bonds, and the hydrogens and the chlorines go on the outside, each making 1 bond. And then for this one, well, you could try and do this, but then what you end up finding is since we're only including 4 hydrogens, we're kind of done, and then this carbon's kind of unhappy with that, right? That's not really satisfying any sort of stability-based rules. But if we tried to move 1 or 2 of them over, this doesn't really help either, but don't forget we do have the capability of making a double bond. And then finally, looking at this structure, what ends up needing to happen is a double bond to the oxygen in this case with its lone pairs, and then, you know, again, everyone is stable, satisfied, filling up those valence shells. So looking back at this, the word usually, and in this case we could talk about all 3 of them, it's not usually, it's always, at least in terms of these 3 particles. Carbon makes 4 bonds and hydrogen makes 1, and that's really important to remember going forward because organic chemistry is a big branch of chemistry. And there's a lot of information on this page. Some of the structures don't even seem, they look like they belong in a geometry class more so than anything else. And then beneath them you've got the names, and sometimes the names are actually longer than the molecules in some cases. And then there's this whole host of ones here where there's a bunch of things that look similar. It's complicated, it's a mess. I do see things like preservatives and plasticizers and personal care products and dyes and pigments. And what's neat about organic chemistry is that's really the branch where it starts intersecting with biology, because a lot of these compounds, yes, they contain carbon, and that's how we're going to define organic chemistry for this course. But, you know, in a larger scope, those carbon-containing compounds interact with living creatures in various ways. And then they do more than that. There's plenty of non-abiotic organic chemistry to consider, but we're not trying to make this too big too quickly. The one thing I can't stress enough is that carbon always makes 4 bonds, period, the end. Now, what's kind of interesting is that because a quadruple bond is impossible, what ends up happening is you can make a triple bond, but then each of these carbons has to be bonded to something else. Sometimes that would be a hydrogen or an oxygen or a chlorine, but a lot of times it's another carbon, and then you'd get more carbons going on and more carbons going on and going out, and all sorts of chaotic, crazy, complex structures. And what that ends up meaning is that organic chemistry, these carbon molecules, these carbon-containing molecules, because of the lack of a quadruple bond, they have to form chains, branches, and rings. And so to look back at this, now you're starting to see some of the chains, the branches, and the rings. Hopefully, if you start to like fuzz your vision a little bit and blur your eyes and squint a little bit, you might get to see that there are some similarities in all these structures, even though they look like a lot of them might be different. So for today, I actually wanted to focus in on one type of molecule, hydrocarbons. This is a creation of polycyclic aromatic hydrogens, completely unrelated to the course, but I just wanted to show you the scope of how many different hydrocarbons they are. From the name, we can figure out that these contain carbon and hydrogen only. Now, it is possible in some of these other structures to see heteromolecules like oxygen, chlorine, sulfur, and nitrogen. Phosphorus can work its way in too, but that's going to make things too complex. We're just going to focus on hydrocarbons for now, and even what we're looking at here is a little too complicated, and I'd rather look at something like this. Hopefully this is a little bit easier to digest. Now what we can see here is we've got 1 carbon, 2, 3, 4, and 5, and then we see there's some structural differences between these. And there's actually some formula differences if you actually counted things up. But I just want to take a second to talk about some of the general properties. Hopefully this one we recognize as something you've seen before, is methane. And methane we know is symmetrical, and then therefore this is a nonpolar molecule. And from that nonpolarity, we get all of the properties that you might expect. We've got low melting point and boiling point. We've got insolubility in water. So these are typically gases at room temperature. These are like methane. These are typically flammable. Whenever they get near oxygen and a spark or a flame, lots of burning happens. And this is actually true of all of the hydrocarbons you see, and hydrocarbons in general. Even though some of them might not look as symmetrical as you might think, they're still symmetrical enough for us to call them nonpolar molecules. It's a weird way of thinking about it, but overall there's still a very even distribution. Even if like molecules like this, it looks like there's an uneven distribution of charge, but keep in mind that even things like this, that's equal sharing, so that's not really going to throw off your molecule. Now here I'm only talking about hydrocarbons. If there's other atoms that get involved, we can definitely get some polar organic molecules happening. And even if we just focus on just the hydrocarbons, all 15 of these are hydrocarbons. So this is already pretty complex and already pretty diverse and already pretty expansive. So I want to give you a chance. Maybe just instead of drawing all 15, maybe draw like the top 6, the top 2 out of every column, because that might help make my point. And for today, we're just going to put all of our carbons in a single line. We're going to make, how do I put this? Oh, I had a good term for it. We're going to make linear hydrocarbons. Aliphatic? No. I mean, yes, but yeah, I think the term there is aliphatic. All right, while you're drawing, I want to I have a hard time with this unit. This is like your low-level introduction to organic, and I'm sorry, it's going to feel like I'm throwing a bunch of words at you. I like organic chemistry, like a lot, but what I like is not the names and not the systems. I like that you can look at a molecule and you can get a feel for how it behaves based on how it's built. It will take us a while before we get into that, and I'd like to get into that eventually, but for now, I mean, like we kind of did in the beginning of the year, we had to learn how to name things before we could, at the same time we're talking about how they behave, and the naming stuff can be a little boring, but it's kind of like your alphabet. You need an alphabet before you're actually going to start spelling words. So to draw these out, C2H6 is going to look like this. Hopefully you drew this. Aliphatic linear hydrocarbons. Acyclic. That's the word I was looking for. No circles. Once you get to C3H6, if anyone drew a triangle, I applaud your inventiveness. Don't do that today. We're not talking about cyclic hydrocarbons today. We might get to that later. We'll see what we have time for. Looking at C2H4, you probably drew something that looks something like this. And looking at C2H2, you probably drew something like this. For organic chemistry, we're going to be slightly lazy. For organic chemistry only, if you draw a molecule that has a line to nothing, we are both going to be in agreement that I understand that you understand that a hydrogen goes there. So the way I drew those 3 molecules is actually consistent with the formulas that are above them. If you were to draw out C3H8, this is going to save you a lot of headache and a lot of letter H's. It would look like that, and we all understand what that means. If you go looking online, you might see something that looks like this for C3H8. You can do that if you think you understand it, but in terms of at least what a Regents class will expect of you, that's too far. That's too many jumps. I won't talk about that to save us all some headache. If you were to draw C3H6, again, some of you might have tried to draw a triangle, but if you don't draw a triangle, you draw this. And then for C3H4, you could have drawn this, or you could have drawn this. We're not drawing allene today, though, so we're not going to look at that one. I want to focus on this one. So now, hopefully, looking at these, what you notice is that in each column, there's actually a bit of a pattern showing up. I see something sticking out. I see that. I'm going to change my color for emphasis. I'm going to use green. I see that, and I see this. And then I see a distinct lack of it over here. So what I do notice is that these all seem to be single bonds. This seems to be a double bond. And this seems to be that these have triple bonds. Now, if you were to keep drawing them, you'd keep seeing that show up, but this is specifically why I wanted to ignore this structure. I don't want to show two double bonds. I want to show the triple bond because it turns out that each of the members of this third column have that triple bond somewhere in their structure. There are other molecules that have that molecular formula, but we're not focusing on those today. And then all of these would have a double bond, and then all of these are comprised only of single bonds between carbons, hydrogens, and carbons. So if instead you wanted to look at, say, the math, there's actually a mathematical relationship. If we chunk these into three groups, there are three patterns. So I want to give you a second to look at it, but try and write a general formula, a mathematical formula describing the relationship between the carbons and the hydrogens in each group. For example, if carbons was like N, then how do I get the number of hydrogens if it belongs to that group? Okay, hopefully I'm gonna start with this one first, this middle one. It should be pretty straightforward. If I have N carbons, it would appear that I have, well, 2N hydrogens. There are twice as many hydrogens as there are carbons every single time. For the first one, it actually turns out it should be 2N, but then plus 2. And for the third one, you get N 2N minus 2. Oops, too many N's. If you got something else that works, I mean, great. These are the ones we're going to go with. These general formulas outline what we call the homologous series. And homologous, like literally breaking down the term, means looks the same. So this homologous series, this formula describes these molecular structures, and so they're related. If you noticed, maybe you noticed, maybe you didn't, new color. It turns out to turn one of these guys, the first column, into the second column, you'll see that adding the double bond, you have to remove 2 hydrogens. And then adding a triple bond from a double bond, you have to remove 2 more hydrogens. Or going from the single bond to the triple bond, you remove 4 hydrogens. And that's where that general formula of 2N plus 2, 2N, and 2N minus 2. For each double bond that gets added into. And it turns out that our reference table is here to help. Before we get into our reference table, I wanted to make the connections to the names that you're going to see for these linear acyclic hydrocarbons. I pulled out 6 examples, and I'm giving you what their IUPAC names are, their official names. So see what the patterns are. I mean, I even bolded certain parts to make it absolutely obvious, but then, so now I think you can tell me, what does prop mean, and what does ane mean? Take a second, think about it. Hit the pause button if you need to look at the slide for a second. But it seems to me that each of these hydrocarbon names has 2 parts. It has a prefix and it has a suffix. And looking at these 3 examples, the only thing that's the same between them is the 3 carbons. So the prefix should represent the number of carbons. Now again, like I said, this is a linear acyclic hydrocarbon for which this is true. And then the suffix actually communicates something as well. This one might be a little bit harder to see what the relationship is, but if you tried to figure out which pattern they belong to, this is the CnH2n plus 2 pattern. So all 3 of these have the same homologous series, And then the 3 examples on the left have the same number of carbons. And so it seems like that's how the naming scheme works with the prefixes and the suffixes. To help out, we have table P and table Q from the reference table. Unfortunately, the organic chemistry naming scheme does not line up with the inorganic chemistry naming scheme at all. So it's a new scheme, but you have your table with you, so it's kind of hard to forget because it's in front of you. So meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. And then what we have is our 3 homologous series are called alkanes, alkenes, and alkynes. Those are like the family names, where the specific names are going to have different prefixes. So for an example, and this is found on table Q, so you can follow along with your reference table, there are 2 carbons, so that our prefix would be eth. This is a member of the alkane, so it ends in ane, so that is ethane. The second example is ethene, and the third example is ethyne. I pronounce it differently to make sure there's a difference between the E and the Y. So as a quick practice, I give you a formula here, C5H10. What is it? Name it. Five carbons. Homologous series name. It's pentene. What does it look like? Well, we're going to worry about that later. We're not drawing a ton of structures today. I kind of wanted to focus on naming them, identifying their homologous series, and then maybe writing a formula from a name. So take a second just to make sure we understand table Q, hit the pause button, go through and figure out which homologous series each of these belong to. I don't need the full name, I need the name of the homologous series. So I'm looking for these 3 as potential answers. I'm going to put myself on the spot here in a minute. So let's see how quickly I can do this. This is alkane. This is alkene. This is alkene. This is alkane. This is also alkane. I have to do math quickly in my head now. 11, 22. This is an alkyne. 18 and 18 is 36, so that's alkane. Hopefully we got the same answers. If I didn't, if I got these wrong, please put a comment below to remind me. So now we can put the 2 together, hopefully taking what we had before and then adding this layer of table P. You should be able to name these. Again, hit the pause button if you want to try and figure it out on yourself. I encourage you to do so. This is good practice. Go ahead and name them. But I'll start writing now. 2 carbons is eth, so that's ethene. 7 is hept. 14 heptyne. This should be hexene. Notice that heptyne and hexene and pentane all contain the same number of hydrogens, but we don't really name it that way. We don't do that here. We really just concern ourselves with what family it belongs to and how many carbons are present. So then this would be pentyne. This would be propene and nonane. Nonane? Nonane? I'm not sure how to pronounce it. I will say that if any of these names are sounding remotely familiar, there's a reason for it. A lot of the alkanes are things that you actually see in everyday life. For example, octane is one of the main components of gasoline. Hexane is a solvent, butane is in lighters, propane is used in grills, methane is found in a lot of Bunsen burner fuels. These substances do show up in a lot of places, and a lot of what we use them for in everyday life, it seems to be like we don't really, I mean, hexane gets used as a solvent to dissolve things, it's polarity, but usually we just use them because they're flammable. So octane, let's break it down. Oct means 8, so we want 8 carbons. Ane means H2N plus 2. 2 times 8 is 16. 16 and 2 is 18. Did I do octane on the previous slide? I did not. I feel like you know what? Nope. Thought I saw it. I didn't see it. That's okay. But yeah, that's how you break that down. And hypothetically, we can go either way. So we can work backwards. I can give you a name and ask for a formula. I can give you a formula and ask for a name. I haven't done this yet. Right. So I gave you a formula and I asked for a name, and so here's a name and here's a formula. So I want to do that too. So say C10, H20. By all means, stop me. Use the pause button. Please stop me. Please get in front of me. I prefer this. Otherwise, I'm just talking to myself. C3H4, C6H14, C7H12, C2H4, and C9H16. So hopefully these are all right. Maybe I made a mistake. I don't know. My brain's starting to turn to mush because I'm doing too much math. So we've got linear, acyclic, hydrocarbons. C and H only, non-polar. Ooh. I need an eraser, clean myself up. There we go. There are still 3 types of linear acyclic hydrocarbons: alkanes, alkenes, and alkynes. I remember it because they kind of go in alphabetical order, and these are single, double, there's like an order to it. Triple. Use table P and Q for now. I mean, later on you might think you've memorized enough to figure it out. You might be doing the math already after just going through the ones that we went through together. But just for now, just use that resource you have. It's going to help make sure you don't make any silly mistakes or careless errors. Thanks for watching.